So now we're on to the next topic. Linear momentum. And linear momentum is going to, okay, this is going to be a pain, so get ready. We're going to denote linear momentum as a lowercase p vector. Okay, we've already used a lowercase p vector, and so you're going to have to differentiate whether you're talking about momentum or position just based on the context of the problem. Okay, I wish we had more letters in the alphabet, but we don't. Uh-huh. Yeah, that's true. That's a good idea. That might revolutionize physics. Um, so the linear momentum is the mass of an object times its velocity vector. And so it's a vector. So it has a magnitude and a direction. Uh, and the direction is the direction of the velocity vector. So the direction is where the object is moving, the direction the object's moving. The magnitude of the momentum and I'm going to just call it momentum a lot, but there is actually an angular momentum too. This is just a linear momentum. But the magnitude of momentum is, roughly speaking, how much it would hurt if the thing ran into you. Okay, so compare, for example, the magnitude of um, let's say the mass is 0.05. That's my guess at the mass of a tennis ball. That would be in kilograms. And a speed of 40 meters per second. Okay, that's pretty fast, almost 100 miles an hour. But it's a tennis ball, so you'd feel it hit, but you'd be fine, you know. Um, so what's that equal to? That's 2 kilogram meters per second. Okay. Doesn't hurt too much. Yeah. And now let's think about the magnitude of the momentum for a Ferrari. How much? What's the mass of a Ferrari? 1,000 kilograms. Okay. I don't know. Let's imagine it's whatever kind of car weighs 1,500 kilograms. Actually, I'm going to make it 1,000 because it's so much easier for me to calculate. And let's say that's going 40 meters per second. Okay, so it's going the same speed, but that mass makes a big difference. And now you have 4,000 kilogram meters per second, and it only hurts for a second. Oh yeah, thank you. That's the new math. Only hurts for a second. Okay, so what football coaches are mostly looking for is they're looking for a bunch of people who, they're trying to maximize the ability to produce linear momentum. They're looking for, like, they like fast people, they like giant people, but what they really, really like are really fast, really giant people. That's where you maximize the momentum. Um, we'll use linear momentum in two results. And both involve, both are useful for impacts, collisions, and explosions. These are the only really useful applications for momentum calculations. The first one is the impulse momentum equation. And it says that the change in an object's momentum is equal to the integral from time 1 to time 2 of the net force with respect to time. And I'll derive that, show you where that comes from. But the first one is a relationship between the change in momentum and forces applied. And the second one is conservation of linear momentum. And that says if the net force on an object is 0, and when I say object, it could also be a collection of objects or a piece of an object, whatever you're isolating. If the net force on what you're isolating is 0, then the object's linear momentum at instant 1 is the same as the object's linear momentum at instant 2. Okay, so conservation means stays the same. So if there's no net force acting on the object, the linear momentum of the object stays the same. So first I'll talk about the impulse momentum equation. And notice that in terms of momentum, in terms of P, we can rewrite Newton's second law as the net force is equal to the time derivative of the linear momentum. Time derivative. Okay, because the linear momentum is the mass times velocity. The time derivative of the mass doesn't change. You know, the time derivative of the mass is 0. And so the time derivative of the linear momentum is just mass times acceleration. And that's what we had before, right? Yes, you can think of this as the time derivative of mass times velocity, and that's just equal to mass times acceleration. And in fact, in Newton's original, his original writing about this gave Newton's second law in terms of momentum. It was later that people started finding it to be efficient, I guess, to think of it in terms of mass and acceleration. But so if you integrate both sides of Newton's second law, with respect to time, you get the integral of F net, let's see, over whatever time interval you're dealing with, we'll call that time 1 to time 2, is equal to the integral from time 1 to time 2 of, right, this is dp dt with respect to time. And then you can rewrite that as the integral from t1 to t2 of f net dt is equal to the change in the momentum over that time interval, or you can also think of that as the momentum at time 2 minus the momentum at time 1. And this is useful for calculating average contact forces over small time intervals. Okay, so let's, how long is this going to take? Okay, so let's say that we want to calculate the what's the average contact force that a baseball bat applies to a ball during a 0.01 second contact. And over this contact, the ball's velocity vector goes from let's see. (40 meters per second) this way. So toward the bat, and this angle is 5 degrees. I guess I'll have to. Am I going to finish this? To 50 meters per second this way, where this angle is 30 degrees. And the mass of the ball is right about 0.1. A baseball is 0.145 kilograms. Let's just call it 0.1 kilograms. Okay, well, notice that over these short duration impacts, you can imagine this average force is going to be pretty big. And in cases like this, a lot of times we'll just leave the weight out of the problem. So the net force is the contact force applied to the ball plus the weight of the ball. Let's just assume that F net is much bigger than the force of the weight on the ball. And so we're going to assume that that net force is really pretty much just the contact force. That's a pretty common assumption. So what we have to do is first calculate the momentum of the ball at instant 1 and instant 2. And then use the fact that the average force relates to the integral of the force, I. So F average times the elapsed time is equal to the integral from T1 to T2 of F dt. Okay. Let's just finish that next time. But that's pretty much the set of steps for any problem you do. Some problems, it might say that you can neglect the weight force. Some problems, the weight force might be more important, so you have to subtract that out at the end. But this is the basic idea. With all the days that have been canceled and stuff, we are a little bit behind, and I'm going to make up some of that time on linear momentum stuff. We're going to skip a few of the problems or parts of some of the problems. And I'm not going to go into detail on some of the things I normally do. I don't think you'll miss it in later classes or anything. But okay, back to linear momentum. Yeah. We should just have like a party, like get those bags where everyone gives each other candy and play music and stuff. That'd teach people to skip class. Okay, back to linear momentum. Um, So there are two results that we're going to use. The first one says that the change in linear momentum is equal to the integral from instant 1 to instant 2 of the net force vector dt. It's important to notice that this is an integral with respect to time. Because later we're also going to do integrals of forces with respect to a distance along an axis. Okay, so it's going to look very much like this, but you're just integrating with respect to a different variable, and it's going to be a totally different quantity that we'll use in other ways. And then the other result, so this is the momentum equation, impulse. And then the second one is if F net is equal to 0, then the total momentum of your system at instant 1 is equal to the total momentum of your system at instant 2. That's conservation of linear momentum. And we started a problem last time. Now we'll go through it. So, yeah, no problem. Okay, so this example that we started last time was a baseball comes in, and I'll give you the angles and the speeds and stuff, and then it gets hit by a bat. We know the duration of the contact. You could tell that from like a high-speed video or something. And from a high-speed video, you can measure the velocity before the collision starts and after the collision ends. And then if you know the mass of the ball, that's enough for you to figure out what the average contact force is, basically. Okay, so that's often a very useful thing. By the way, these are always used in collisions, impacts, and explosions. There really are not many applications outside of those things. So like as we go on and we learn more techniques, more physics approaches to problems, it can be a little bit of a challenge to figure out, okay, all these numbers and things are thrown at you. What technique am I using here? Well, this is the answer here. So if you remember this, you'll always know when to use a linear momentum approach. Yep. The conservation of linear momentum is the one that probably are applications to the first one, but I'm not really sure what it is. But conservation of linear momentum is really useful with explosions because an explosion is all internal forces, so there's no net force acting on the object. And so if this thing explodes and you can measure the momentums of the pieces after the explosion, you know, or some of the pieces, you can figure out the momentum of the other piece or something. Yeah, so the system is what it originally started as, and then instant 2, you're talking about these 4 chunks that are flying off or something. Yep. Mm-hmm. Yeah. They're sort of the same thing, I guess. I'm including impacts in there to include things like bouncing off the ground or a wall or something. You don't, we don't sort of naturally think of that as a collision between two objects because the wall doesn't really move at all, at least in our calculations. So that's an impact between the thing that you're calculating and then the thing that's basically at rest. Yeah, where the masses of both of them and an impact. I don't know, I just made these terms up, but an impact, I'm thinking of one thing that you're measuring the mass of and one thing you're just assuming just stays there. Like when you land on the ground, it really is a collision between you and the earth, but the earth moves so little that you don't really include that in your calculation. Okay, so our example says, um, so here's a bat. It's swinging this way. The ball's coming in this way. Um, and then pow. And then after the collision, you know, the ball has a different velocity, and we want to figure out um, so we want to figure out the average force applied to the ball by the bat. So before the collision, we'll say that the ball has a velocity vector of 40 meters per second, 5 degrees below horizontal. And after the collision, it's moving at 50 meters per second, 30 degrees above horizontal. And we'll use the mass of a baseball. It's really 0.145 is the required mass of a baseball, but let's say that the mass is 0.1 kilograms. And we want to know what's the average contact force applied to the ball um, assuming it's that contact force is much larger than the weight. It wouldn't be that hard to include the weight in there, but you can imagine over this very short duration of contact, uh, like if the ball was a person worrying about its health, it would be very unconcerned with the force applied by gravity. And over that 0.01 seconds, it would be very concerned with the force being applied by the bat. Um, and this impact takes 0.01 seconds. Okay, so the first thing we have to do is figure out, well, we're going to use the impulse momentum equation that says the change in linear momentum is equal to the integral of F net dt. And this really useful fact that we're going to use is if you're only concerned with the average force, because that net force is going to change, at the first instant of contact, it's not going to be a very large force. And then as the ball compresses, that force is going to get bigger. And then as it starts to leave, it's going to get smaller again. But we're just going to assume that it's constant the whole time with a value of F average. And then this is just equal to the average force times, T2 minus T1 and this is just the elapsed time. Okay, so at instant 1, the momentum is, our coordinate system is like this. The velocity vector is 5 degrees below the horizontal, and the magnitude is 40 meters per second. So you can think of that as that velocity vector is 40 times cosine and sine of 185. Yes. Can someone plug that into a calculator and tell me what that is? I think it is now, yeah. Okay. Okay. And so, yep. And the linear momentum is just that times the mass. And so that's just equal to negative 0.3905, negative 0.0348. And the units are kilogram meters per second.
It's 0.1.
Mass, thank you. Yes. So this is negative 3.905 and negative 0.348. Yes. And, I don't think I can really help you that much. I mean, you can remember what the units are just by the definition of the thing, because you're just multiplying a mass times the velocity. And kilogram meters per second, the best I can say is like, if you think of intuitively what momentum means, you think of it as like big fast things have a lot, small slow things have a little, then that's about the best I can do. Uh, that was your idea, right? The squiggly under squiggle on the, yeah. I'm going to do that to differentiate momentum from position, but I've never done that before. You don't have to do it, but the thing is, you just have to be careful because now we have a vector quantity called position and a vector quantity called momentum, and they're totally different, and they have the same, they're represented the same. Okay, so that's the momentum at instant 1. And then at instant 2, our velocity vector is 50 meters per second. The angle here is 30 degrees. And so the velocity vector at instant 2 is 50 times cosine and sine of 30. And that is 43.3 and 25. And then the momentum at instant 2 is the mass, 0.1, times the velocity at 2, And so you get 4.33, 2.5. And now the impulse momentum equation says 4.33, 2.5, the momentum at instant 2, minus the momentum at instant 1, which is negative 3.905, negative 0.348. Is equal to the average net force times the elapsed time, which is 1 seconds. Okay, so what's 4.33 plus 3.905? 8.28. And then what's 2.5? Well, I can do that one. And then the I component is 2.85. And then I'll multiply that by 0.01. No, sorry, divide by 0.01 seconds. 0.1 is the mass, and 0.01 is the elapsed time. And this is equal to the average net force. And so that's 828 newtons in the x direction and 285 newtons in the y direction. Okay, this is the average net force. But if you think about, what's the force applied by the weight on this ball? It's 9.81 times 0.1, so 0.9 something newtons. And so we're just, not even going to bother in this case with subtracting that off, but it's not hard to subtract it off if you want to. It just takes 1 Newton away in the y direction, or I suppose adds 1 Newton in this case.
How you get the 0.01?
That was given.
Okay. Oh, yes.
Can you explain a little bit, quickly, the impulse momentum equation?
Yeah, that's the one that says the change in the linear momentum is equal to the time integral of the net force. And if instead of trying to figure out the whole shape of the net force, you're just trying to figure out the average net force, then the change in linear momentum is equal to the average force times the elapsed time. And so that's what we did, was just put all those values in there. On the ball. Yep. Because the mass that we used was 0.01. And we didn't know the velocity of the bat. So you have to know the momentum of your system before and after the collision. So our system had to be the ball. That's what we knew the velocity of, and that's what we knew the mass of. Yep, that's right. Yeah, it would be really hard to do it with the bat. So, I mean, you can, I think, see the usefulness of that if you're trying to figure out, there's going to be this impact in whatever system you're designing, and you need sort of a ballpark figure for what that impact force is going to be. you can calculate that just from measuring the velocities before and after. And by the way, I did this with assuming a constant net force, F average, but you could assume any shape you want and match your results to that shape. You could assume that the force is going to ramp up from 0 at the beginning and end of the interval to a maximum in the middle, and you could fit the rules for the area of a triangle to it. I'm not going to go through that, but it would probably take maybe an hour, maybe 2 or something, but you have the ability to think through that if you were interested, which I'm not implying that you should be, but it's not hard. Because so this is the impulse momentum equation, and we're trying to isolate this, so I'm just dividing both sides of the equation by 0.01.
That gives you that. The left side gives you the average, right?
The left side is the change in linear momentum.
Okay.
We calculated that, and then we divided by 0.01 to isolate the average force.
But wait, where does the 1? I don't see the 1 in there.
What one?
It adds up on the left side, but when you're divided by 0.01, how'd you get divided by 1?
No, multiplying by 1 over 0.01 is the same as dividing by 0.01.